Good morning, students. So this is a continuation lecture on the models of neural networks. So at first we have discussed what is a perceptron, and then now here in this lecture we will discuss logistic regression. Um, this logistic regression, if you see how it is different from perceptron, the only thing that is different here is like what activation function we are using here. If you remember that in perceptron we have used a step function rather than a sigmoid function. So here all things are same like perceptron. We have a node, and this in this node what we do, we take a dot product of weight vector with the input vector x. So just recall, like x is an input vector which can be an image, right? So image, if we take an image and flatten it into a vector, so then each pixel will be input feature for this node. So from x0 to x12287, these are all pixels aligned in a vector form, vertical vector form, and then each pixel is getting multiplied with some weight w0 to w12287, right? So if we write it in a linear algebra form, it is nothing but we are just doing a dot product with x vector with a weight vector, where weight vector is nothing but it is from w0 to w12287, and where x is nothing but x is a vector that is having from x0 to x12287. So these are the two vectors, and in linear algebra form, if we multiply element wise, we can write it in a transpose form or a dot product form, which is nothing but w transpose x. And then after taking a dot product, we are adding bias to it, w, and then we are applying some non-linearity here. Then in perceptron, if you remember, the non-linearity which we had applied was a step function, right? This was a step function which we had applied. Here, rather than applying a step function in logistic regression, we applied a sigmoid function. So if you see this sigmoid function, how can you see it? It sandwiches all numbers from minus infinity to plus infinity between 0 to 1. So let's say on this x-axis, I have all real numbers between minus infinity to plus infinity, and anytime you feed a number, it always sandwich between 0 to 1. So for example, here minus infinity is mapped to 0 and plus infinity is mapped to 1. So this a is nothing but it's a real number, and if you feed the number to this sigmoid function, which look like this in mathematical notation, so if you feed any real number to this function, it give you some number between 0 to 1, right? It give you some number between 0 to 1. The cost function that we have here is different than what we had used in perceptron. If you remember, in perceptron we had used error function, which was nothing but a sum of all misclassified errors with negative notation. But here in cost, the cost function that what we used in logistic regression is this: a negative log of probability of a target vector, right? So if you remember that in perceptron we had a number between, we had either +1 or -1 as a prediction, but now here onwards we can see the output as a probability. Why we can say that it is a probability? Because every time you feeds any input vector x to a say logistic regression, it will take a dot product with w, then it add a bias, then it take a dot product with input vector x, and it add a bias, and what it will do, it then feed to a logistic sigmoid function. It will map this number from between 0 to 1, and you know the probability is always positive and between 0 to 1, so we see this output as a probability. So now what we say that we take the negative log of the probability of a target vector, right? It will try to gauge like what is the error of this function, right? What is the error of the input in the prediction? For an example, let's say you have an image which is having um, label 1 for the cat, and for dog, let's say it is having label 0. So now if you feed this cat vector to a logistic regression, it, let's say, produce some number zero point 0.7, right? When you feed it to this, when you get a prediction zero point 0.7, you, and the expected was 1, right? Because the true label is 1. So it means there is some difference, and the difference is nothing but it's an error. So it means you are bit far from 1, and this is then you can see it as an error. Similarly, for dog image, if you feed this dog image to a logistic regression, let's say it predict point 0.8, but you are expecting 0. So there is a big difference between 0 and point 0.8, because your prediction is more near to 1, and but the expected output was 0, right? So this is again a difference. So now to to calibrate this error, to gauge this error and then fine tune a model, we need a error cost function. So this cost function, what it says is that it's a cross entropy. Actually, it's a cross entropy. And if you see it one by one, for an example, you are feeding a um, cat vector to a logistic regression, then it means your true label is 1. It means your true label is 1. So then Tn, which we have shown here, is a true label. So for cat, Tn is equals to 1, and for dog, your Tn is equals to 0. Why we have used n here? That is it for nth sample or nth image. So just for now, just you can ignore this n, because we are talking only a single sample. So now in case of cat, my true label is 1, which is t equals to 1. If you feed it into this cost function, because my label is only, I have only single label, let's ignore this summation, because this is error for all the samples over a data set. So let's say I have one sample in a data set. Now that is only a cat. So if I feed a cat to my logistic regression, what is the error? It means my Tn will be 1, because my true label is 1. Then 1 minus Tn will be 0, because true label is 1. So 1 minus 1 will be 0, and this term will go away. And this term will go away. So the only error that I'm having will be log of my prediction. Let's say the prediction is 0.7. Then I will say 1 multiplied by log of zero point 0.7, and this negative is already there. So it means my total error, how I see it, is log of 0 0.7, right? Now let's say like I have only one sample, which is dog. I have only one sample, which is dog, right? And if I want to see like what is the error in case of a dog, if I feed my dog to the logistic regression, I get zero point 0.8, right? But the true label for this dog is 0, right? So if I feed this again to my error function, my true label is 0. It means my first term will go away, because t1 equals to 0, and 1 minus t, which is 1 minus 0, is 1. It means I am getting here 1, and this is log of 1 minus my prediction. The prediction is 0 0.8, so it is 0 0.8, right? So it means the total error is I am having is log of 1 minus 0 0.8, and this negative sign, which is already there, will come here. So this is my total error for the dog classification, right? So if we just further simplify 1 minus 0 0.8, it is nothing but log of 0 0.2 of negative log 0 0.2. So if you if you calculate error for every sample, and then finally you will add these total errors. So this is a total error over a data set, right? This is how we can calculate a total cost or total error over for my predictions. Now once I calculate the total error for my prediction, what I will do, I will take the derivative of this error function, as as we know, like what we need to do is we apply a gradient descent over this cost function, right? So this is my cost function. I know that I want to take a derivative of this cost. I want to take a derivative of this cost function, and then after taking a derivative, what I will do, I just update my w new, w new, w old, some step size, and derivative of the error function, right? The derivative of the error function. So this is my error function. I need to take a derivative. First I calculate a derivative and then plug it here. This is nothing but it's a learning parameter, right? This eta is a learning parameter, which is a step size. So I have already discussed in my previous lectures. Please go through those lectures to understand this further. So now the only thing left is how to calculate the derivative of this error function with respect to your parameter. So because in logistic regression, I have, if you remember, just to recollect, these are my W0, W1 till some W, till W and capital M, let's say. So there are M parameters, let's say. So you want to take a derivative of this error function with respect to every W in the parameters. So how to do it? So the this error function, you just apply a chain rule. So this is your error, what you are getting here at the end at the output. You take a derivative of this error with respect to this output, what you are getting, because output you are getting in terms of a y, right? This is your prediction. So first you take a derivative of error with respect to y, then y, how you are getting y, you take a derivative of this y with respect to this input before when you apply before this a is nothing but it's like what you have feed to a sigmoid function. So because this a you got and then over a you applied a sigmoid function. So just to show you computationally clearly what we have done here is computational graph. So this was your logistic regression. In logistic regression, uh, there was your feeding input vector x here, right? And each input vector, each pixel is getting multiplied with some w till wm. Let's say there are m parameters and there are m features, right? For every feature there is a parameter. So x0 is multiplied by w0, x1 multiplied w1, and so on, and xm multiplied w1, and then you add it, which is nothing, and then you added a bias, right? So which we called it as a here. So a is w transpose x plus b. Then over a, what you did, you applied a logistic regression, which is giving you a y, right? So now because we want to take a derivative of our error, and once you get a once you get a prediction y, then your error was what? This was your error. You feed this prediction into this function and you get an error. So step by step, what you do, you just take a derivative of this error function with respect to y, okay? And then this is the first step. Then you take a derivative of y with respect to a n, right? So you take a derivative of this y with respect to a, and finally you take a derivative of this a with respect to w. So right, there are three steps here. So the once you take a derivative of respect with a, then you get this value and this value respectively, right? Well, if you multiply all these three values, what you will get, you get this quantity, and it is nothing but it's a derivative of e with respect to your w parameter, w, right? Why there is summation? Because for every sample you are doing it, so there are n samples. So then this because it's a linear summation, so all derivative get added which you are calculating for every sample, and then you plug this and then you plug this derivative into this equation, which is nothing for where you are calculating where you're doing a gradient descent. So this derivative, you feed it here. This is a step size. This was your old w, and this is your new w, right? We have discussed it before, right? So gradient descent, I have already explained what it do, because if it will converge to a local minimum. If you want to do it in your computer, let's say if you want to implement a logistic regression, I just take an example. Let's say I have a MNIST data set, which is a very standard data set. You can find it out on internet, right? So in MNIST data set, there are 60,000 images, and each image contains digit from 0 to 9. Let's say I take one image which contains 4. I flatten this image, and I feed it to this input, right? And these are my some random weight vectors, which may not be correct in my first iteration. I just take a dot product, I feed it to a sigmoid function, I got some output, expected output, I got some prediction, that is zero point 0.6, right? Zero point 0.6. And because I was expecting, I am discussing binary classifier, so here let's say I have two sets of images, either it belongs to 4 or it belongs to 0. So let's say for 4 my label is 1, and for image 0 my label is 0 itself. So because I was predicting, I was feeding 4 and I'm expecting 1 here, and I'm getting zero point 0.6, it means an error. I will take a derivative and then just back propagate it, right? How to do it? Because this MNIST data set, I just said that like I have filtered only those images between 0 to only those images which contain 0 and 4, right? So you take a 4, let's say it's a two-dimension image, so then you just flatten this image into a vector form. So you just take 1 2 3 4. If it is two dimension, you just convert into a one-dimensional vector, right? And if you have some 60,000 images or some 100,000 images, because each image is of 28 by 28 pixel, when you flatten it, it will convert into a 784 into one vector. Now what you will do, you just you just put each image into a column, right? Because just you represent vector, you represent an image through a vector. Now this vector is nothing but an image, so you just put first image in first vector, first column, second image in second column, third image in third column, and likewise if you have m images, then the mth image will be in the last column. And what is, and for every image you have some label. So then you take a second matrix y, and this dimension of this matrix will be 1 by m. So here then this label for first image, the label for second image, and so on, the label of the mth image. So this is your expected output, right? Which is a true output, which is available in a data set. How to do it? So I said that like you take a dot product of your weight vector with all the images. So you are just doing in one shot everything, right? Because x is what? It was a column vector. Every column is having an image, and you take a dot product with your weight vector. Weight vector is common for all images, right? So you just take a dot product with first image, you get a first prediction. You take a dot product with second image, you get a second prediction. And like we use for mth image, for mth image you take a dot product, you get mth prediction, right? So this is a matrix for your prediction, and here we call it as a. So this a, and you apply a sigmoid after it, right? After putting a bias, after adding a bias. So for prediction, so you take a dot product, then add a bias for every prediction, and then for every number you are applying a sigmoid. So you applied a sigmoid over this, you applied a sigmoid over this, you applied a sigmoid over this. So finally you are getting a predictions here, right? This matrix we are saying it as a here. So this is an a, and we have just this is your cost function, right? If you take a derivative, we have just said that like how to calculate a derivative. This is the form of a derivative, right? So this we have calculated in last email. So if you calculate a derivative of a cost with respect to your w, this is what derivative will be. And this is a derivative for your bias, right? And you just plug this derivative into this equation for gradient descent, and it will be only a one iteration. So if you do it repeatedly from 1 to n iterations, you can train your logistic regression, right? Uh, so this was just only a one neural network. We have discussed so far. We have used perceptron. In perceptron, the activation function was a step function, right? Then we have discussed logistic regression. The activation function was a sigmoid there, and now you can generalize it. So if you just take more than one from one node, if you go to three nodes, right? If you go to multiple nodes now, right? And if you go to multiple layers, then you can form a different architecture of a neural network, right? It depends like how many layers you want to take and how many nodes in each layer you want to take, and it will construct a different architecture, and it will give you a more different computation power. You can train each of the model. We will discuss like how to train these kind of networks in the next class, right? So after this, I will be like arranging one discussion class. If you have any difficulties, we can discuss it there. Thank you very much.